All right, welcome everyone to the afternoon parallel sessions. I'm Kevin, I'm just emceeing this. So let's get on to the really important stuff. This session is about evaluating player and team lineups, and our first presenter will be Devan Becker, and Devan is nearing the end of his PhD program in statistics at the University of Western Ontario. His primary research is actually in looking at quantifying the dependencies between all the different forest fires and the size of those fires. And of course, when he likes to relax like we all do, he likes to spend that long day fitting spatial models to mostly hockey data itself. So without further ado, let's welcome Devan.
All right, thank you for that. So I'm here from Canada, so I'm the token Canadian talking about hockey today. I am from University of Western Ontario, which is in London, Ontario, which has the distinction of being the second best London in the world. So yeah, like he said, my main work is in forest fires. I'm looking at complicated spatial models, as well as some other sorts of models that I'm trying to fit joint distributions between a bunch of different factors, including the spatial location. I was watching hockey one night and realized that there's lots of location data in hockey. I wonder if that data is available. I searched for it for a long time and eventually found some. And so I've got Calgary Flames shots versus Maple Leafs. This is where all of the shots happened, and then this is fires versus leaves. And they're basically the same models can be fit to both, which is one thing academic statisticians are always about. We have a model, let's find data, rather than possibly the right way to do it, which would be having data finding a model. But I've got a hammer, everything's a nail. So today I'm going to talk about an NMF LGCP algorithm. This is non-negative matrix factorization for log Gaussian Cox processes, which is just a lot of really fun, fancy words to say. I'm going to look at NHL shot data, and I'm going to show a little somewhat clever way of finding shot efficiency. There's some issues with this data. It's not the easiest data to work with, and so I had to do it a little bit my own way. So the central idea behind this algorithm is I've got a bunch of spatial estimates, and I treat these spatial estimates as images to put into an image recognition algorithm. So I've got this X matrix is just each column is the pixels of a spatial estimate, and I want to split that into two separate matrices. The first one defines the building blocks, and the second one is how much of each building block a given estimate uses. So this is quickly stepping over a lot of the really complicated stuff. I'm using log Gaussian Cox process estimates of the shot locations, which comes with its own difficulties and advantages. I'm going to skip over a lot of the math. This is actually my only equation in this. That was really hard for me to do. I wanted to do more, but I was advised against it. This is a very quick overview, so I'll give a little bit more of an example. So I've simulated 4 players that have obvious shooting locations. It's just so I can make sure that my algorithm is doing exactly what I think it is, and I can see by eye that, yeah, there are 3 locations. I fit a spatial estimate. My research is actually just going from this top row to the second row, and that in terms of forest fires, this is something that's really important to do. In terms of shot locations, the interpretations of the variance and whatnot aren't as important to most people. I find outside of stats, most people don't care about variance as much as I try and tell it to them at a bar. So I take these images, and now what I do is these images are treated as the data. So I forget that these ever existed, and now I'm just dealing with the images. It's just a bunch of pixels with some grayscale value, just an intensity surface that I can now put into one big matrix and split into 2 matrices. And so this is what those 2 matrices will look like. I've got basis 1, which is just shots from here, basis 2, which is just shots from the left point, and basis 3, which is shots from the crease. And so instead of having 4 pictures, I now have 3 pictures and a couple of numbers. And so I've cut down my data quite a bit. I've summarized what's going on the ice. Player 1 is almost no shots from basis 1, a couple of shots from basis 2, and mostly shots from basis 3. And that's exactly what's going on here. The left point and the crease, and basis 2 and 3 are left point and the crease. And so I'm satisfied that my model is doing what I think it's doing. And at this point, I want to say the coefficient, the value of the coefficient isn't overly important to interpret. It's more how much of each coefficient each player uses. And also, when I fit these images, the grayscale values are all normalized so that I'm not looking at any information about how many shots they took. I'm not looking at any information about how many of those shots were goals. I just have the estimates of the images. It's just a grayscale. It has no information about the number of shots or anything like that. And so it all works nicely when I know exactly how many bases are supposed to fit. So in this case, there was obviously 3 bases. In real data, it's not so obvious how many bases to fit, how many building blocks go into making it. If you use too many, it becomes a model for noise, and that's overfitting is a big issue in this sort of image recognition. If you don't have enough bases, then I'm not characterizing things the way they should be. And if I have the right amount of bases, I can start interpreting what those bases mean, especially in terms of the spatial point process algorithm. I can see what each basis is representing. And if I know that I've got the right amount of bases, then it's important. This is not something that's super simple to do, so I'm just going to go over it quickly. Skip over it quickly, rather, apparently. So this is a quick description of the data that I'm using. I scraped it from this mysterious API. There's no documentation for this anywhere on the internet. Nobody put any press releases out when something new comes out. Nobody explained what the links mean. Somebody just found it one day and started exploring it and posted their updates on GitHub, and eventually it became a thing. It's also a lot of it's been scraped and put on Kaggle, so if you're looking for this sort of information for yourself, there is a Kaggle data set that has all of the event data for NHL. I took all of the event, so it includes things like where they got hit, where a fight happened, where penalties happened. I'm just looking at the shots for this, but it's got that information if that's something you're interested in. I split it up so that I've only got players with more than 500 shots, and that's a lot of shots. That's since 2011 that they've had that many shots. So one of the big problems with spatial estimates is you need a lot of data to get a reliable estimate. Otherwise, you're essentially modeling noise. You can imagine if you only have a couple of shots, it doesn't define a pattern. And I also removed rebounds, which is an ideological choice. I see rebounds more as an opportunity rather than setting up as a sort of strategy. And the location of a rebound is always going to be in front of the net. It doesn't matter if it's on the side of the net or directly in front of the goalie. A rebound is a rebound. The spatial locations aren't as important to me. So I've got 466 players in my data set and over 500,000 shots still, so I'm not cutting my data down too much, I don't think. So this is what the bases look like. I chose 7 because they do have nice interpretations, and I also looked at a lot of the statistics that you're supposed to look at for non-negative matrix factorization, cophonetics and residual sum of squares, and all those sorts of things that don't need to be explained for this to be interpreted. So this is just, I took a bunch of images, and this is what the computer saw. I didn't tell it where to look for anything. I only told it how many bases to look for, and this is what it tells me. So the crease is an obvious place. People shoot from the crease. This is just what if you're modeling shot locations and you don't have one that says crease, you probably didn't model them that well. The slot is also an obvious place to shoot from. Interestingly with this, the left crease and the right crease got split out from the main crease. So these are separate shot locations that different players tend to use. When the right crease got split up, it actually included a bunch of area on the left ice. So this is very likely forwards who are shooting from over here and then sometimes going for a rat run, going around the net, trying to surprise the goalie by coming to the opposite side. And so these bases are actually inferring some sort of causation, or not causation, some correlation of where different shots are taken from. So players that tend to shoot from here also shoot from here. And so that's already some interesting things. It doesn't apply to the right ice as well. So there is still a little bit of mass to the left of the crease on the right ice, but not nearly as much. I believe this is mostly because a lot of hockey players are left-handed, and so when you're shooting left-handed from the open ice, and then you go around to the side, you've got a nice way into the net, which doesn't apply to players on the right side of the ice. You can't go around and dump it in the net from the surprise side as easily. So that's something interesting as well, that I've got this open area on the left ice associated with the crease, but on the right ice, it's more or less on its own. And obviously the points, which are just basically there for completeness. Defensemen shoot from there and mainly there, and that's going to show up in the data. And so those are the bases. I've also got the coefficients that I can look at. I've got Ovechkin at the top row for all of these plots. Ovechkin is a left wing who shoots right-handed, and he shoots mostly from the crease, but also a lot from that left crease, just directly to the left of the net, which makes him a little bit different from other players since he is right-handed, which means his body is actually mostly behind the crease as he's shooting. He shoots a little bit from the left ice, and the right crease, but not as much, and he shoots from the slot. We've also got PK Subban, who is a defenseman, so he mostly shoots from the points. Not included in this analysis is where he fights, but that would be a more interesting analysis for him. And then I've got 4 centers. 3 of them are left-handed, 1 of them is right-handed, so Getzlaf is right-handed, and he shoots from the left crease, which again, like Ovechkin, makes him a little bit different. Shooting right-handed from the left crease is not common. And then I've got 3 players who are centers who are also left-handed, and so if this was all that explained their locations, their position, and their handedness, you'd expect them to be very similar, but we have Ans Kopitar shooting a lot from the right ice, which is not something a lot of other players do, and it's kind of giving us some insight into his strategy. He's definitely a little bit different from other players. I think that's all I want. And he also doesn't shoot from the crease, which is really weird. But he still makes it work, which is the interesting thing. I can throw all of these coefficients. So now for each player, I've got 7 coefficients that define where they shoot from on the ice. They have a fuzzy boundary. I'm not partitioning the ice based on any sort of imposed ideas. It's just a computer saying these general regions, and then I've got coefficients for each one. I'd like to have a way to compare players. So one way is to reduce the dimensionality using principal components, and looking at what the outliers are just to have an idea of what this algorithm's picking up. And so these aren't players I chose, these are just outliers according to some algorithm. And we see some familiar names if you're familiar with hockey. Obviously, Ovechkin and Thornton and Kovalchuk are important names. Some of the centers and especially some of the defensemen, I don't know who these players are. I've never heard their name that I can remember, which just goes to show being different doesn't mean you're good, is kind of the point of this slide. Which goes into what does mean you're good. So just being different isn't good enough. I want some measure of shot quality. So after me is Nathan Sandholz, and he's got basketball data. It's a similar-ish algorithm that he uses, but he has a bit of an advantage over me with his data. I looked it up for players who played at least half a season. The worst three-point percentage is about 30%. So even the worst shooter for basketball is making 30% of the 3 points. The absolute best shooter for hockey is only making 23%. So I can't just look at a player where they shoot from and where they score from and compare those directly. I do not have enough data for that. If I take a broader view, I can look at shots that didn't go in, all the shots that were saved. These are not missed shots or blocked shots. These are just shots that were saved versus shots that went in. And this basically just, the only conclusion to draw from this is shoot from close to the goalie, which is not advice any hockey player wants to hear. They'll just get mad. And so I want some balance between this, specifically where does this player shoot from and where do all players score from. So my idea was to bring in perfect players, which is I'm assuming that there's some disembodied entity that inhabits a player just to make them score, and every goal comes from that one player, whereas when a player misses, you can blame that player instead of invoking spirituality. So I'm taking all of the goals as if they're from one player. So I've taken all of the shots from all players and all of the goals from as a single player in the analysis, and then I can get the coefficients for this perfect player who always scores, and I can use this as a comparison measure. So these are the coefficients that I get when I do that. Everybody shoots from the crease except for defensemen, which is obvious. This is just where goals are essentially scored from. Everybody scores from the slot. It does, for right wing, it doesn't quite matter what hand you are, but for say, centers. Right-handed centers tend to score more from the slot. Left-handed centers tend to score from the left-handed crease, which is why I was talking about Ovechkin being a little bit different, and he's right-handed and scores from the left crease. Right-handed left wingers are the only ones who score from the right ice, which is interesting because they're the only ones who do that. It really depends what your handedness is, but this might also have to do with coaches' choices of where to put right-handed and left-handed players based on their position. And there's some obvious differences between left-handed and right-handed defensemen. They just tend to be put in those locations. But what this gives me is an idea of not just shoot from here and you will score, but an idea of shoot from these general areas. Shoot from here more than you shoot from there. Try not to shoot from here a little bit. They're not prescriptive of a single point on the ice. I'm not splitting up into tiny little bins and saying, these are the good bins to shoot from. I've got a nice heuristic description of all of the ice locations on the ice and an idea of what percentage to shoot from each location. So this can be used to inform the strategy quite a bit more. And so a little bit of a case study. I've got Stastny, Crosby, and Daho. So this is the coefficients for the center, the left-handed center again. And Paul Stastny tends to shoot from basically the same places, except he shoots too much from the right ice, it would seem. And when I looked him up on eliteprospects.com, their description was he could stand to shoot more, which my analysis tends to agree with. Sidney Crosby doesn't shoot like a perfect player. He shoots from wherever he wants to shoot from, and he scores from wherever he wants to score from because he's he's Crosby. I'm looking at the wrong. I changed the players just before I did this. And Sebastian Aho, I have him on here because he screwed up my analysis a couple of times because there's 2 of them in the NHL, and I joined data sets based on name instead of ID, which is a lesson I won't forget. So I had to rerun all of the analysis because of him, so I wanted to shame him. This is the one that plays for the Hurricanes. He doesn't tend to shoot from the same places. He shoots too much from the right crease. He's shooting from the point as a left-handed center. He's not shooting from where my analysis says he should shoot from, and his description is he's a very good passer. So I've got 3 examples on here. Stastny tends to shoot from where he should, and he doesn't score as much as he should. Crosby doesn't shoot from where my analysis says he should, and he scores a lot. And Aho doesn't shoot from where I say he should, and he doesn't score a lot. So this doesn't in itself say that this is a good way to measure what kind of shot quality they have. So I looked at just shooting percentage versus the distance between these two. So I've got 7 coefficients. I can look at the Euclidean difference in Euclidean distance in 7 dimensions and look at them that way. And I do find in all cases, to differing degrees, if you shoot closer to what the perfect player does, you tend to score more goals. So again, this analysis took out all of the information about how many shots they took. It took out all of the information about what goals they scored. And I'm able to recover that just based on where they shoot. So I do have a method that I believe does say something about where you should shoot from on the ice. It has some good interpretations. It's not perfect, but it says something nice. So some of the conclusions are just, with these bases, I've got foundations for advice. You can look at this sort of thing, look at where your player's shooting from and say, maybe you should try shooting from different locations or get yourself into position to shoot from different locations. The coefficients are a nice way to talk about strategy broadly on the ice. And I still find it really interesting that the bases include the left ice and the right crease, or the right ice and the left crease, treating those as a single location rather than imposing any beliefs on it. The perfect players are somewhat of a measure of quality. They're not a perfect measure, but it does give you some starting point to say what players should do. If players have different, I don't believe a computer should ever make decisions for humans, so I can point this out to coaches and say, if your player's shooting from the wrong locations, maybe tell them to shoot from here. If what they're doing is working, then go ahead. I'm not God. And so lastly, I'd like to acknowledge this alphabet soup of funding organizations. This work is still ongoing a little bit. I've got some ideas of how to make things a little bit more precise in terms of, if I go back here, skipping through is a good idea. This is measuring something like 400 goals per pixel on this image at the highest. So when I'm looking at these perfect players, I actually have quite a few goals to work with. So I'm looking for some ideas of how to split this up a little bit more. And I can say the perfect player after a pass across the blue line, or the perfect player after somebody else gets hit in the middle of the ice. And I can split things up a little bit more like that. And the spatial statistics behind this can be made to be a little bit more complicated. It's already starting from a complicated place, but there's some more things I can do with that. And so I'm going to stop rambling about what I could do and just thank you for listening. I don't know if it's a good thing or a bad thing that I've got that many questions.
First, thank you. This is a bit of a tangent. There's a tension in hockey between wanting a clear path to the goal and wanting to take advantage of screens.
Yes.
Do you have any comment about that?
This analysis, my data can't tell me anything about that. The data that I have just says there was a shot at this location, there was a pass at this location. I have no information about where anyone else was. So it's, I can try and watch the game that the data comes from and see if locations match up, but it's hard to fit that information into this sort of algorithm. So it's a general strategy rather than when there's people or when there's not people. It's try to shoot from these locations, try to get these locations open.
Does your data differentiate between shots during a power play or five on five?
I used all of the shots. I could differentiate based on that, and that might be one of the extensions of splitting it up a little bit more. But there aren't a whole lot of shots on power play that I can use. By definition, there's at most one goal per power play, maybe two if it's the other team scores a goal. But yeah.
So I've got three things. One is in your basis.
Yes. I'll bring those back up.
Looks to me like the slot and the crease have same area. I mean, they cover
Yes.
the same area. So shouldn't those be unique? I mean, how do you determine between in the slot and the crease? That's where their hot spots are.
Yeah. So this is one of the interesting things about this is there's allowed to be overlap. I'm not partitioning the ice. There is allowed to be overlap. So players that tend to shoot from here also shoot from here, but then there's another class of players that shoots from here and doesn't shoot from here. So
In that dark area, how do you know whether it's a crease shot or a slot shot?
that's a good question. There isn't a distinction from the way this algorithm is treated. The idea behind this analysis is essentially every goal or every shot, you choose randomly from one of these bases and then choose a random location based on what the basis describes. So I might say this shot's going to come from the crease, I might say this shot's going to come from the slot, and then choose a location based on what the basis says.
Okay.
But it doesn't work the other way. It doesn't say this shot came from this basis. It's choosing this basis and then a shot from within it.
And the other thing I was surprised by, Ovechkin's data shows that he doesn't shoot from the left ice. He's classically known for that goal from the left ice. That's what he's known for. So I'm surprised it doesn't show up in the analysis. I mean, the left ice shot is that's his bread and butter on the power play. I'm surprised that doesn't show up in the analysis. He scores a lot from that left ice shot. I'm surprised. And then the last thing, I guess, I'm not surprised that when a player shoots from the perfect player spot that he scores a lot, because the perfect player scores every shot, right?
Yes.
So that's where all the goals come from. So only when he shoots from that spot is he going to score, because by definition, the rest of the spots have no scoring.
Exactly, yes. So there are still goals from other places. It's just the algorithm is picking up the most common places to score from.
Doesn't the perfect player account for all the goals?
Yes.
So any time you have to shoot from it, the shooter has to shoot from where the perfect player shot to score, because the perfect player describes all the goals. If you don't shoot from where he shot, you're not going to score, because he counts for all the goals, right? Or am I missing?
There is general trends rather than shoot from this exact location. So, yeah. It's trying to figure out, since I can't do goals divided by total shots, I have to say goals as locations, general locations. And then, yes, that player always scores, but perfect shots, perfect players are always a subset of other players. So it's, yeah.
So a common saying in hockey, especially when like a team is struggling to score, they always say, get more pucks on the net, get more shots at the net. You never know when a goalie's going to make a mistake or he'll give up a free rebound or something to that extent. So would you say in your studies you found that, I mean, I don't know if you went to this extent, but you found that less shots of a higher quality is necessarily better than more shots of a lesser quality?
My analysis doesn't say anything about whether that's true. I would agree that generally putting more shots in the net has a better chance, but I think my analysis is saying the location does matter. Don't just shoot blindly. A lot of it is also strategy rather than just where you shoot from. It's getting to the locations.
One question for your statistical models. So how about maybe the performance? If we would create maybe 7 dummy variables in that surface, if use these 7 dummy variables to fit the LGCP, how about the estimated performance of this data?
The residuals will always go down, no matter until I've hit the number of players with the same number of bases. If I have 1 basis per player, then obviously it's going to fit perfectly. I start to lose information from each basis, and it starts to look like every basis looks like this, where it's just bumps everywhere on the ice, and I start accounting for every single shot. There's some measure of cross-validation score that goes into it.
We have time for one more question.
How did you handle tipped shots in this data? Do you know how they were handled? Was it a shot from the point as well as a tip in the crease, or how was that handled?
I removed those because it's hard to say where it was shot from. The data just says tipped shot, and it shows them all directly in front of the net. And so that's nothing to do with strategizing the location to shoot from. It's just having the right person tip it in. And in the data itself, that's recorded as a goal by the person who tipped it. And so I don't know who shot it. I don't know where it was shot from. So I can't include that data.
Great. Well, let's thank Devan again.